how do we interpret the exponential of a matrix? Let's call the matrix A. So we want to find e to the A, the exponential of this matrix. Well, we have to interpret this as a series. So we are going to sum with the index n going from 0 to infinity, a to the power n over n factorial. Now, this is a good interpretation because I have simply expanded in a series this exponential, and here I have powers of a matrix, and I know in principle how to calculate these powers because I simply have to multiply the matrix by itself n times here, and as n grows larger I have more and more multiplications. So it might be complicated in general to find the exponential of a matrix if we rely to this formula. We understand the meaning, but it is not so easy to calculate the exponential from this formula. So one way to tackle the problem is to rewrite the matrix A in diagonal form. So A will be equal to some matrix lambda times a diagonal matrix times lambda inverse. This is one way to rewrite the problem by using diagonalization. So that's what we are going to do. And if we rewrite this problem by using diagonalization, we are going to sum from n equal to 0 to infinity, and then we have here in the numerator we have products of this form, lambda times d times lambda to the minus 1, then I have lambda times d times lambda to the minus 1 dot 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 lambda times d times lambda to the minus 1, and this is a product which contains n times this factor. So this appears n times, and then I have to sum over n. And also remember to divide by n factorial here, right? But why did I write it like this? Well, because you can see that here you have something which simplifies. You have lambda inverse times lambda, which is the identity, and then here you will have something similar between other two factors, and so on and so forth. So these terms will all simplify. They will become the identity matrix. So we can rewrite this summation, this series, in this fashion. We can rewrite it as sum with n going from 0 to infinity, lambda times d to the power n, because all these d's here will multiply, and then I have lambda inverse over n factorial. So I can put lambda out of the summation, and also this lambda inverse will go to the right. So I can rewrite it as lambda times sum with the index n going from 0 to infinity, d to the power n over n factorial lambda inverse. But what is this? This is simply e to the d, the exponential of a diagonal matrix. And in here you can see that I simply have to multiply diagonal matrices, and that's very simple, that's very easy, because I simply have to multiply the terms on the diagonal with the terms of the diagonal here. So this term will multiply this one, and this term will multiply this one, and these products will be very easy to calculate. So I can write e to the a like this, lambda times e to the d lambda to the minus 1, so lambda inverse. And e to the d is very easy to calculate. So if I have, for example, a 2 by 2 matrix like this, d1, d2, 0, 0, if I want to calculate the exponential of this, it will be simply equal to e to the d1, e to the d2, 0, 0, like this. And then I will multiply by two matrices, lambda and lambda inverse. So in principle, this is very easy to do if we diagonalize our matrix, instead of doing it by using this formula here, because in principle I have infinite products to calculate, so that's not feasible. But let's consider an example. So we will apply these concepts to one example. I will consider 2 by 2 matrix of this form, A equal to 2, 1, 3, 0, and we want to find the exponential of this matrix. First, we have to calculate the eigenvalues. So we calculate the determinant of the matrix 2 minus lambda, 1, 3 minus lambda. So this is simply how these eigenvalues are calculated. Also, the concept behind eigenvalues are quite simple to understand and to explain, but I'm not going to do it in this lecture. And now we calculate the determinant. We have 2 minus lambda times minus lambda, and then I have minus 3 equal to 0. From here you get lambda squared minus 2 lambda minus 3 equal to 0, and this will give us lambda equal to 1 plus or minus square root of 1 plus 3, and therefore we have two possible eigenvalues. One is equal to 3 and the other one is equal to minus 1. So let's calculate the space for the so-called eigenvectors. So we want the eigenvector space. How do we find it? We have to consider the matrix A, and then we subtract lambda times the identity matrix. So let's choose 3 first. Here I'm going to replace lambda with 3. And therefore this is equal to minus 1, 1, 3, minus 3. And how do I find the space of the eigenvectors associated with the eigenvalue equal to 3? I simply consider this same matrix, minus 1, 1, 3, minus 3, and then I multiply it by a vector xy, and I set it equal to the null vector, 0, 0, to the 0 vector. And this system has a determinant equal to 0, and so you can see that this matrix has a determinant equal to 0. It's easy to see. Therefore, you will only find a solution, an equation from this system of two equations, so only one independent equation, and this equation is minus x plus y equal to 0, which means that y is equal to x. So you can choose, for example, the following eigenvector, 1, 1, because we know that y must be equal to x, and we can choose this eigenvector. We need another eigenvector associated with the other eigenvalue. So the other eigenvalue is lambda equal to minus 1. So we have a plus I, which is equal to 3, 1, 3, 1. And we do something similar. So we have 3, 1, 3, 1 applied to the vector xy and set this equal to the vector 0, 0. And from here we also get only one equation of this kind, 3x equal to minus y. So we can choose the eigenvector 1, minus 3, for example. So our matrix lambda is simply given by two columns, and these two columns contain the two eigenvectors that we just found. So we have 1, 1, 1, minus 3. And our diagonal matrix would be the matrix 3, minus 1, 0, 0. And we know that we also need lambda inverse. How do we calculate lambda inverse? We start from this matrix here, and there are different ways to calculate the inverse. I'm going to use one very well-known algorithm, which does something like this. So we start from this matrix, and we start from this element, and we cancel this first column and this first row. So we get minus 3, and we have to rewrite minus 3 here as the 1, 1 element. Then we do something similar for this element here. So let me go back and cancel that. So we have minus 3 here. Then we cancel this column and this row. So we will be left with this element. So here I will put 1. Something similar for here, this element here. So we cancel this column and this row, and we will be left with this element. So I will put 1 here. Then we do something similar for this. We cancel this row and this column, and we will be left with this element. So I will have 1. Now what I have to do is I have to change signs to this element and this element here. So I will have -3, -1, -1, 1. And I have to take the transpose of this matrix, but the transpose is equal to this matrix itself because it is symmetric. And then I simply divide by the determinant of this matrix here, which is -4. So I have times -1/4 because I have to divide by the determinant. So the determinant is -4, so I multiply by -1/4, like this. And this is simply lambda inverse. So you can check that lambda inverse times lambda gives us the identity matrix. It's quite simple. Now, if I consider the matrix A, the matrix that we started from, so this matrix was 2, 1, 3, 0. Go back and check. 2, 1, 3, 0. If we apply this matrix to the matrix lambda containing the columns of eigenvectors, the first column is 1, 1, and then we have 1, -3. This is equal to the matrix lambda 1, 1, 1, -3 applied to the diagonal matrix 3, -1, 0, 0. So you can check easily that these two are equal, and this is related to the concepts of eigenvalues and eigenvectors. So if we take the inverse of this, it will appear here, which means that we have lambda inverse A times lambda equal to D. Or if you want, we can take the inverse of this and put it here, and we will find the equation A equal to lambda times D times lambda inverse, which is something that must be respected, something that must be satisfied. Here you can see the equation that we have to comply with. And therefore, now we are ready to calculate the exponential of our matrix A, the exponential of 2, 1, 3, 0, which is equal to the matrix lambda, which is 1, 1, 1, -3, and then we have to exponentiate this diagonal matrix, which is easy to do. So we have e to the third power 0, 0, e to the -1, and then I multiply this by lambda inverse, which is this expression here, and I can rewrite it by multiplying this factor with all these elements. So I can rewrite it as 3/4, 1/4, 1/4, -1/4. Now let's multiply these three matrices. First, I multiply these two, so I will have 1, 1, 1, -3, and here I will have 3/4 e to the 3, 1/4 e to the 3, 1/4 e to the -1, -1/4 e to the -1. This is equal to 3/4 e to the third power plus 1/4 e to the -1. Let's split the elements of this matrix. Then I have this row multiplying this column. So I have 1/4 e to the third power minus 1/4 e to the -1. And then I have 3/4 e to the third power minus 3/4 e to the -1, 1/4 e to the third power plus 3/4 e to the -1. Simple as that. So we have found the result. The exponential of this matrix is still a matrix, and it has the following form here that we just found.